All right, just like electric fields, magnetic fields store energy. So you can think about the magnetic field as being a real physical entity because there is energy stored in space where there is magnetic fields. And one way to get at that is to consider the energy stored in an inductor in a circuit because it turns out that energy is stored in the magnetic field. So if I consider a simple circuit where I have a battery, we're going to do this circuit in detail in class, a switch, put a resistor here, and then I have a coil. Okay, and that coil has some self-inductance value L, which again, remember, L just tells me the relationship between the flux through the coil and the current in the coil. Okay, so EMF here. When I throw the switch, current's going to start to flow. But the way you think about this circuit, as we'll discuss, is that the battery is doing all the pushing. It's going to push current. And so the battery gives energy to, say, electrons that are going to be moved around the circuit. And they use up their energy going through different circuit elements. So they use up energy going through the resistor. That turns into heat, that energy. And they also have to use energy to go through the inductor, okay, especially at the beginning. When I just throw the switch, what we're going to find, and we'll derive this in class, is that the current as a function of time will increase and then come to steady state with time. Okay, won't jump up suddenly to some finite value. And the steady state value will be the EMF over the resistance. Okay, and the reason it doesn't come up quickly is because you have this back EMF that's in this circuit, and this back EMF due to the inductor goes like minus L di dt. Okay, so this is working against the current. So it's the current's trying to build up. This back EMF is trying to stop it. So the battery has to do extra work against this inductor in order to push a current. Okay, so that energy, there's an energy that goes into that, and you can write it as the energy spent across a circuit element is just the potential drop across a circuit element times the current that's flowing, or better stated, the EMF in the case of the inductor times the current. Okay. So that amount of energy has to be spent to push current through the inductor. The inductor doesn't want current to go through it. It doesn't like changes, okay? And so as you're trying to change the current through the inductor, it's resisting that by through this back EMF process. And so you have to push hard enough to get the current to go. And so you have to expend energy. And the question is, where does that energy go? So in the case of pushing current through a resistor, it's very clear. The energy goes into heat. So you have to push it through the resistor. There's collisions that happen. Those collisions transfer energy to heat. In the case of the inductor, what you're doing is charging the inductor. Okay, so charging the capacitor makes sense because you're actually putting charge on the plates. When I say charging the inductor, what you're doing is building up the magnetic field inside of the inductor. So it turns out that the energy associated with magnetic field can be written as the following. So I can write an energy density for the magnetic field, and it goes like B squared over 2 mu naught. Should look familiar if you remember the electric field energy density. If I have both E and B, the energy per unit volume goes like the following. Okay, goes like the square root of the field strength times a coefficient to get the units right. So epsilon and naught and mu naught are there really to get the units right. Okay. Excuse me. Okay, so this is the energy stored in magnetic field. So what I want to do is just show you that that's connected to this case. I jumped ahead a little bit here. So I want to consider this a little bit further. Okay, so let me go to the next page. And if I write down, so this is going to be the power expended at any point in time in the inductor. So that's going to go like minus Li di dt. I'm just replacing the EMF. Okay. If I want to know, so this is the power. Okay. If I want to know the energy that has been used up because of pushing current through the inductor, I just integrate this with time. Okay. All right. Now this minus sign comes about. That's the push back from the from the inductor. Really, I have to spend an amount of energy that's the positive of that. Okay, so I'm going to change the sign here, but this EMF is the inductor pushing back. You're going to push in the opposite direction to get the current to go, and so the work that you do, really the battery does, will be positive in this case. And you can integrate this. This just becomes, I can basically cancel that out, and I have integral of I di, and that's going to be 1/2 I squared. So I'll have 1/2 Li squared. So that's the energy stored inside of an inductor given a certain amount of current I flowing through it. And as I was saying before, this is stored in magnetic field. Okay. I should just say B. Okay. Now, I'm not going to prove that to you, but I'm going to show an example where it all works out. So I just wrote down that the energy density, this is energy per unit volume in the magnetic field, is B squared over 2 mu naught. Okay, so what I should be able to show is that if I can integrate all the magnetic field energy in space, and that's what I have to do, because the magnetic field might go on forever, right? In other words, if I have a simple loop here, the magnetic field reaches off to infinity, and I would have to integrate over all of space. Okay, so really, the energy stored by magnetic fields due to a current in a coil, I have to integrate over all of space to count that up. Okay, so I want to see if that is equivalent to that. Okay, so let me take an example where I can do this, and that's the case of a solenoid. Okay, so I'm going to do two calculations. The first, I just generated a video that showed that the self-inductance of a long solenoid is mu naught number of turns squared over L times pi a squared. Okay. And so therefore, if I have a certain current flowing, I know that the energy stored in that inductor, the energy required to charge the inductor. Again, let me go back and point at this graph. That's on the previous page even, sorry. When I'm all done, so with this process of charging my inductor. So basically it takes time to get the current to build up. And in that time I'm spending energy to build up the magnetic field. But when I'm all done here, the inductor is no longer pushing back because the current is now steady. And I've stored a certain amount of energy in the coil at that point. So that's the energy I'm thinking about, is the energy associated with that magnetic field that's driven or produced by the current in the coil. Okay, and that's going to be 1/2 Li squared, which, if given our expression for inductance above, I get mu naught n squared pi a squared over 2L, where L is the length of the coil, times I squared. Okay. All right, so that would be the energy stored in a long solenoid because I have I'm driving a current in it. Okay, so this, again, I think about this as having to push against the back EMF of the inductor, and that energy I spent is what I've written here. Okay, and now I want to show you that that's what's stored in the magnetic field, which I can do fairly quickly. The magnetic field inside the solenoid I can write as mu naught n times I. Okay. So now if I calculate the energy density, okay, so the magnetic energy density, and this is uniform everywhere inside. Of course, it goes in the z-hat direction up the solenoid if the current is flowing in the right direction. But the energy density doesn't care about the direction of the field. It's just going to be B squared, which is mu naught squared, n squared, I squared. Okay. Now over 2 mu naught. Okay, so that's B squared over 2 mu naught. This is the energy density per unit volume, or the energy per unit volume, which is the energy density. So it's mu naught n squared I squared over 2. Okay. All right, now to get the total energy, I have to integrate this. Wherever there's magnetic field, I have to sum it up because this is the energy per unit volume at a location. So it's going to be the integral of U over the volume. But because the field is uniform, this becomes straightforward. I just have the energy density times the volume where the magnetic field exists. And that volume is just going to be energy density times pi a squared L. Okay? And so if I put all that together, I find that the total energy stored will be mu naught. And let me do this. I'm going to turn little n squared into big N squared over L squared. But one of the L squared is going to be canceled by the L over here. Okay? So I'm going to have it over 2L times I squared, and then times pi a squared. Okay? And you can see that now these two expressions match. And so at least for this particular case, I've demonstrated that you can think about the energy, again, fighting against the back EMF is how you spend energy to push the current through the coil. But we can see that if I believe that the energy density of the magnetic field is B squared over 2 mu naught, that's consistent with the fact that the energy is stored in the magnetic field. So the idea is that you've put energy into the magnetic field, which I can get back later. As if I discharge the coil, in other words, if I lower the current in the coil, there's going to be a back EMF that will prevent that current from lowering, and that will try to keep the current going. So an inductor, you can use that energy to push current later on, and we'll talk about that in class. Okay, I'll stop there.